Welcome to the TWIML AI Podcast. I'm your host, Sam Charrington. All right, everyone. I am here in Vancouver at the 33rd NeurIPS conference, and I've got the pleasure of being seated with a repeat TWIML guest, Sergey Levine. Sergey is an assistant professor in the Department of Electrical Engineering and Computer Science at UC Berkeley. Sergey, welcome back to the TWIML AI Podcast.
Thank you.
So your team has been, continues to be very productive and prolific. You've got a dozen papers submitted here or accepted here at the main conference, as well as a number of workshop papers. And I would love to use this opportunity to kind of get caught up with you and hear about what you've been excited about recently. I think it was July. Well, not I think. I just checked, actually. It was July of 2017 that we last spoke on Deep Robotic Learning. What have you been up to? What are you excited about?
I guess a lot has happened since then. Broadly speaking, a lot of what my lab has been trying to do since then is really to try to move towards sort of a future where we could have machines that are out there in the real world learning continuously through their own experience. And while we're doing a lot of very different things, in many ways, much of this work is centered around the components that we believe are necessary to make that happen. So I could tell you, for example, about some of the things in this conference that I'm pretty excited about, that I think are giving us sort of a non-trivial step towards that direction.
Absolutely.
So one of those things is basically techniques for combining model-free reinforcement learning with planning. So this is something that I think is actually a really big deal. You know, conventionally, when we think about rational decision making, we think about kind of a planning type process. You know, if you're imagining how you're going to get to the airport, you think, well, maybe you'll get the train or get the taxi. How do you pay for the taxi, or how do you pay for the train? You know, what do you do when you get there? And there's a sequence of steps that you have in your mind. But the thing that's always been kind of puzzling is that those steps they're a little bit abstract. So you don't plan how you're going to move every muscle in your body in order to get on the train. You plan through individual steps. And that has always been the big challenge in marrying planning and learning, is that you can't plan over the low-level kind of instantiation of your behavior, and it seems like learning doesn't by itself give you these kind of planning-type behaviors. So we have actually two papers in the main conference that study different facets of this problem, essentially using learning to learn behaviors that achieve goals, and then planning over the instantiation of those goals to achieve much more temporally extended outcomes. And I'm pretty excited about that because that gives us some ideas about how reinforcement learning can, in a sense, almost provide the abstractions over which planning can be done.
What's the relationship between planning and model-based approaches where you're integrating in some, prior knowledge about how a task should be performed?
So planning is typically regarded as a very model-based thing. And I think that one of the things that's kind of an interesting shift away from the conventional way of thinking is that conventionally people think that, well, planning is this thing that you do. Well, first people think that it's something that you do, that you publish in kind of dusty old robotics venues. But they think it's like this thing that you do on top of a very physics-based, manually designed model. You open up the physics textbook, write out the equations. And I think, my group is not the only one working on this. I think this is actually something that we've seen come up more and more over the past year or two, is that people are thinking, well, can you learn abstractions that you can plan over that are not just purely predictive models? So these abstractions don't try to predict, if you take this very low-level action, here's what will happen immediately at the next point in time. But they're kind of higher-level abstractions. They're like, if you execute this intention, how will the world change in some representation that sort of lifts you away from the low-level physical grounding. And by lifting you off from that low-level physical grounding, you actually get a much easier planning problem. So in effect, learning serves to simplify the planning by putting it into the right abstract representation.
And why is that? If the planning still needs to be done at a low level, so, in theory, to actually, move the robot or get us from point A to point B?
Yes, exactly. So in effect, the learning kind of takes care of the low-level details. So if you have a model-free learned behavior for, let's say, walking to the door, then you don't have to plan how you're going to do that. You can plan at the level of, I want the door open, and then kind of, let your body do its thing to get you there. And I think that's kind of the intuition behind how these methods work. They let the learning take care of these low-level details, and then remove them from consideration for the higher level planning. So it's a kind of a hierarchical approach.
I was just going to ask that. It sounds like you're proposing a hierarchical approach in which, as opposed to assuming low-level physics-based models, for example, you're maybe learning in both levels of the hierarchy, but the hierarchy itself simplifies does it simplify both or just the higher level problem?
So the hierarchy simplifies the higher level problem, but it does in a sense simplify the lower level problem, because now the learning component doesn't need to take care of being able to achieve very temporally extended goals. So often in reinforcement learning, one of the hardest things is if you have a task where you don't realize that you've reached a successful outcome until you've performed a very long sequence of behaviors that are by themselves unrewarding. So in effect, by chunking up the problem into these intermediate sub-goals, which the algorithm can basically invent. So it basically makes up, like, here are some places I could go. For each place that I've reached repeatedly, let me just compartmentalize that into a little skill. So that doesn't require achieving any temporally extended goal, like getting to the airport. And then the higher level planner can go in and say, oh, you know how to reach all these sub-goals. Let me figure out how to sequence them so that you accomplish your end goal. The notion of hierarchical learning like this is not by any means new, but one of the things that has been sort of coming to fruition recently is that people have figured out how to abstract away both the behaviors and the states, right? A planning problem consists of states and the actions, right? So the actions get abstracted away as these skills, and the states get abstracted away via representational learning. And if you have both of those, then you can get a substantially simplified problem for the higher level planner, and you can actually get some of these things to work on interesting, like image-based tasks, for example.
One of the interesting nuances that came out for me in the way you describe that is when we think about the analogy that you used, I want to get to the airport, I need to take the bus and the train and the taxi, whatever. That is maybe, let's say, a top-down kind of plan. I'm thinking, I start by identifying the intermediate states that are going to get me to the end goal. But what I thought you just said was that perhaps the intermediate states can be learned in the process of, you're still specifying the end goal maybe, and the intermediate states are learned. And, I'm almost thinking like they become kind of a compact or a better optimized representation of memory. There's a lot of work happening here to try to, in RL to incorporate different memory schemes so that we're not throwing away what we've learned in the process. This is perhaps
a little bit. So there is always, for any hierarchical scheme, there's a top-down and a bottom-up component. And I think it's conventionally actually something that's been a lot more common is to think about it mostly as a top-down process. So there's a single task that you want to accomplish. It's a very complex task, and you'll go in and sort of chunk that task up into pieces.
Yeah.
But what has really worked out much better, and this is what we use actually in our work in the main conference too, is that the discovery of the behaviors works very well when it's bottom-up. Essentially, if you go and try to do something in the world, and in the process you've accomplished accidentally maybe something else, like maybe, I'm trying to get to the kitchen, but I happen to have figured out how to reach the bedroom. I'm not thrilled about that, but I can sort of file that away as something I've learned to reuse later. And this bottom-up discovery of skills ends up working very well for these kinds of hierarchical methods, because you can discover those skills before you actually know how to solve some really complex tasks.
And so is this analogy to memory one that's useful, or?
Yeah, I think so. I think in effect, everything that you experience in the course of solving whatever tasks you have to solve in the world, even if it's not useful to that task, you sort of file it away in your memory as behaviors that you can draw on later. And in practice, the way we represent this is not quite so discrete. It's actually a continuous space of all the possible goals you could reach. And you can think of this as basically filling out that space. So for all the possible states you've seen, can you get a behavior that reaches them? And it's a continuous representation, not a discrete one.
What did you call this particular kind of line of research?
We don't really have a clear name for it, although maybe we should. So we don't call it hierarchical reinforcement learning because the higher level here is not really reinforcement learning. So I've been calling it kind of hybridizing planning and learning.
Okay.
To me, like the important bit about it is that the learning provides the abstractions to the planning. So maybe I should come up with a name for it that reflects that.
Okay, and so that's a couple of the papers that you have.
Yeah, so we have two papers on this. We have one called Search on the Replay Buffer by Benjamin Eisenbach, which applies kind of a non-parametric graph search approach to it. And then we have another one called Learning with Goal Condition Policies by Sarusha Nasseriani, which applies more of a continuous trajectory optimization approach for the higher level, so where you continuously optimize over goals.
Mm-hmm. And so are they, it sounds like they're both, they're alternate approaches to the higher level optimization problem as opposed to kind of picking off small pieces of...
Yes. So the lower level skills actually in both papers are built by learning goal conditioned policies with RL. And that's a technique that has been explored in prior work too. So that's in some sense, it's very important, but it's not really the new part.
Cool. So that's 2 of the 12 papers.
Yeah.
What else?
Yeah, there is another thing that I could tell you about that is maybe a little bit outside the norm for what we typically do, because it's not quite so focused on autonomous robotic learning, but it's a topic that I think was very interesting to work on, and maybe something that could be interesting to your listeners too. So we had a presentation. This was actually an oral presentation by a student who was actually a visiting student with us named Pim DeHaan. And what he worked on was understanding the role of causality in imitation learning. So, causality is obviously a big topic. I'm sure you've had guests on your show who talk about it.
Not enough, though.
Not enough. It's something that it took me a while to understand why this was important. And for that project, we really wanted to isolate...
Well, let's pause there. What did you learn after the while? What was your realization about why it's important?
Yeah. So I guess maybe to answer this, I should first say why I was not sure that it was important before.
Please.
And the reason that I think this is actually a fairly typical doubt that comes from reinforcement learning researchers.
And to kind of go back, inside the onion one more layer, maybe, a summary of causality and kind of, how do you describe, causality?
Well, so a causal model is a model that associates causes with effects, whereas a correlative model is just a model that tries to notice that, when 2 things seem to occur together, you can guess in your data what the value of one of those things will be from the value of the other one. But if the relationship there is not causal, that doesn't necessarily mean that when you see new things, that the same relationship will still hold. To use an example that's maybe a bit more relevant for our work, if you imagine a driving scenario, you have a car, the car in front of you stops, that causes you to stop. But if you stop, the car in front of you will not necessarily stop. It just so happens that if you look at data, almost always, if your car stops, the car in front of you stops, but the causality goes the other way, right? So there's a correlation in the data because people don't just stop for no reason, but you can't exploit that correlation to affect change in the world. And that's tremendously important for robotics, of course, because the whole point is to do things that affect change in the world.
But you didn't think that was important for a while.
I didn't think that was important for the following reason, which is that if you train predictive models and you use those models to act, then maybe your models will make mistakes, but when you go and use them to act, if you actually try stopping to get the guy in front of you to stop and you notice that it isn't working, then you will update your model.
You'll learn that.
Yeah, you'll patch up that hole. And that's why I said earlier that oftentimes reinforcement learning researchers maybe don't worry about these things so much, because once you're in this sort of closed loop scenario where you're constantly updating your model, maybe those correlations very quickly get fixed up and turn into causal relationships, because otherwise you make mistakes and you have to fix those mistakes. But we did figure out a particular setting where this is very important, that is actually a setting where the issue even comes up in practice, like in actual practical things that are deployed there in the world right now, which is imitation learning. So imitation learning is a very simple and very powerful tool that people use today for things like autonomous driving and many other robotics applications, where you collect data from a person operating a machine, maybe driving a car, and then you just treat that as a supervised learning problem. So predict the action the person took from the observations, which seems like a great idea. Like for driving, you get lots and lots of data doing this. But there are all sorts of correlations that happen, like that stopping example that I gave. Another correlation could be that maybe you turn on the turning signal when you're about to turn, and then you turn. But of course, the turn signal is not what caused you to turn. What caused you to turn is your intention to make a right turn. And that's perhaps a bit risky. Typically your camera in your car will be mounted outside the car, but if it happens to be inside the car and it can see your turn signal, then it might decide, well, I'll just wait for someone to turn on the turn signal before I turn, which makes no sense, of course. So there are all sorts of these correlations that can happen. And the way it shows up in practice is that when people add more inputs to their system, maybe they have a camera, they'll also add history, or they'll add LiDAR, or they'll add some other sensor. They sometimes find that their imitation learning system actually does worse. And why does it do worse? Well, because all those additional sensors that they're adding add more potential correlations, which might result in this causal confusion. So one of the things that we did with PIM is that we worked on formalizing this problem, identifying why it happens, where it happens, reproducing it kind of in a little petri dish in some toy domains, and then coming up with some simple causal discovery techniques that could be used to partially address it. So our solution is not perfect, it doesn't fix it every time, but to me the thing that's pretty exciting about this work is that it actually allows us to make a little bit more formal something that people have observed anecdotally before, which is this phenomena that adding more information into your imitation learning system makes it do worse. And I'm pretty happy with that work because I think it's also a technique that people are using in the real world, and if they're not aware of this issue, they might get into a bit of trouble.
Can you give us a sense for the technique itself, what it's doing?
Yeah, it's actually kind of neat. So this was something that Pim and Dinesh, the lead authors on this, came up with. The idea is that you can think about discovering causal graphs. So if you have a bunch of variables, let's say you have a discrete set of variables, the variables you're predicting are the actions, the variables that you're observing are the observation variables, the states, and some of those state variables are actual causes of the actions, and some of them are spurious. Some of them you should not pay attention to, like the turn signal or whatever. Now, the trouble is that if your observations are things like images, you can't just treat every pixel as a possible cause. There's a lot more structure underneath. So what they did is they actually combined a representation learning phase where you actually take your observations and you turn them into a smaller set of independent latent variables with a causal graph discovery phase. So they have one model that learns this representation, these disentangled variables, and then they have a second phase where they train a model that takes in those variables and a mask that represents the graph. So the graphs always map inputs to outputs, so basically you can represent all possible graphs with a vector of bits that says which edge is there and which edge is absent.
So is the graph learned, or is the graph imposed?
It's actually a little weird. The model actually simultaneously represents all possible graphs, which seems really hard because there are exponentially many graphs. But of course, the wonderful thing with neural nets is that they do generalize. So it turns out that you don't have to have it train on every possible graph to get it to generalize meaningfully to all or most possible graphs. So you basically randomly delete or remove edges and then train it on these randomly selected graphs and then hope that it generalizes to the others. And so long as those training graphs are drawn from the right distribution, then you should get generalization if you sample enough graphs. Now that doesn't let you discover the right graph, it just lets you compactly represent all the possible graphs. The discovery then requires intervention. So to discover which of those graphs is correct, you have to somehow break the correlations in your data. So you do that by actually attempting the task, but a very, very small number of times, just so you can figure out which of those graphs is the right one. And those attempts can have one of two forms. Either you attempt the task and you ask for additional human supervision. So you say, well, if I were in this intersection, how should you drive? Or you assume that you have access to a reward function. So you try it yourself and then you look at the rewards. Of course, in both cases, you could learn the task entirely from scratch if you have enough interventions. But the point is that if you have these pre-trained candidate graphs, you can discover the right one with a very, very small number of interventions.
Okay, I'm trying to wrap my head around all this. It sounds like, if I'm understanding what's happening, that the training effort is like some exponential multiplier on the training effort for, not trying to figure out this causality. Like in other words, a lot harder, because you have to, it's almost like you are coming up with this graph and then applying like a dropout kind of thing where you're breaking these connections, and you've got to, and the graph is potentially, you have a kind of end by end fully connected thing. I'm imagining it exploding.
Yeah. Well, so the reason that this ends up being not exponentially difficult is that there's a bit of regularity. So if there's a particular variable and you include that variable or exclude that variable, while in principle the behavior of the resulting model depends a lot on all the other variables, in practice you can generally get a pretty good idea for whether that variable is a cause or not, just from whether it by itself is excluded or not. So if you exclude, for example, the extra turn signal input, and things just kind of work, okay, maybe the right graph is like no turn signal and some of these other things. But just from the fact that you included the turn signal in these 5 graphs and excluded it in these 5 graphs, that's a really good hint that the turn signal should not be included. So while in theory the whole thing is exponentially bad, in practice for most problems that's not usually the case, and you can identify these individually. So that's why we can get away with substantially less than exponential time training for this, even though in principle there are exponentially many graphs. Of course, you can construct pathological problems where this would not work. So if there's some very, very specific set of edges that works and everything else fails, then through random sampling you probably won't discover that.
Right. You mentioned that you formulated a toy problem to illustrate this. Presumably that's also the problem that you presented your experimental results in the context of. Tell us a little bit about that problem.
It's actually a very simple toy problem. We just took an Atari game and we drew on the screen a little number that indicates what action was taken at the last time step. You'd think this would be completely innocuous, like this is the action, you already took that action and you just draw it on the screen. But for good Atari playing strategies, usually the current action is strongly correlated with the previous one. So if you're moving the Pong paddle down, you probably move it down for several steps. So there's a strong temporal correlation, which means that drawing that previous action as a digit on the screen gives the imitator a very strong hint about the next action. But of course, that's not a causal relationship because the action you took before is not the cause of your next action. And so it turns out that just adding that digit to the screen for an Atari game completely breaks your ability to imitate an optimal Atari player, which is kind of a disturbing thing to me.
Yeah, why is that? Is it because the agent kind of over indexes on the thing that you drew, or?
Yeah, it's because basically learning machines like to be lazy if they can be lazy. So a very lazy strategy is to just say, hey, I know that the next action strongly correlates with the previous one. Not always, but it's a pretty good clue. So it's very easy for me to read this digit. It's very hard for me to figure out what's going on in the game. So I'll just start off by looking at that little hint that you gave me, and I can get some decent performance out of that. And I'm so happy with that I'll kind of not really pay as much attention to everything else and never bother learning the real task. So it, of course, doesn't pay attention exclusively to that thing, but it pays so much attention to it that once that relationship is broken, once the action is not actually coming from an optimal policy, once it has to play for itself, the performance just tanks.
And so since you're optimizing on the ultimate outcome, it's kind of like, in a sense, a crude sense, like a multitask thing. It's like find an optimal policy given the previous action.
Well, there's an important distinction, which is that imitation learning is not explicitly trying to find the optimal policy. So this is one of the things about imitation learning that's a little bit of a shortcoming, but it's why it's so simple, is that imitation doesn't care about what's good or what's bad. It just cares about what the demonstrator did.
Okay.
Which is great because you can train it from data without all this complexity of reinforcement learning. But it's not so great because, of course, it can't understand what's optimal and what's not. It just says, did you do it and can I copy it?
Yeah, I'm still trying to kind of narrow down what exactly we've done by drawing the number because we already knew the thing that the agent is trying to imitate is what was done.
Yeah, it kind of seems like it almost shouldn't change the problem.
Yeah.
But the subtlety there is that the data that you trained the agent on all came from your expert demonstrator. So while when the agent is playing the game itself, that previous action indicator doesn't really give it any additional information, when it's trying to copy the expert, it does actually give it a bit of additional information because it tells it that the action that the expert took in the previous state, which is probably pretty similar to the current one.
So does in the otherwise formulated imitation learning problem, the agent doesn't have access to the action itself. It has access to the observation of...
Yeah, so it's supposed to predict the action from the observation. So in the same way that an image classifier predicts the label from the image, this thing predicts the action from the image.
Yeah. What other interesting things are you presenting here?
So there is one more thing that maybe would be interesting to discuss a little bit, which is some work by a student named Michael Janner studying model-based reinforcement learning.
Okay.
So model-based reinforcement learning is something that we often think about as being kind of a more efficient but perhaps somewhat more complicated solution to reinforcement learning problems as opposed to model-free reinforcement learning, right? In model-based reinforcement learning, you first learn how to predict the future, and then you use that predictive model to actually act in the world to accomplish some task. And what Michael wanted to understand is, can we actually analyze the degree to which model-based reinforcement learning provably results in a better policy at each iteration? So there's been a lot of analysis in model-free RL, particularly for policy gradients. So we did some work, for example, back in 2014 with John Schulman on the trust region policy optimization algorithm, TRPO, where we did analyze that under some circumstances you provably get an improvement in your policy. Admittedly, under some assumptions that are pretty strong, like having infinite samples, but it's a beginnings of a theory. But such a thing did not exist for model-based RL, and one of the things that Michael and the other students on the paper were able to figure out is that you can actually write down a similar kind of theoretical proof that given enough samples, model-based reinforcement learning will produce an improvement at each iteration. And how much of an improvement it achieves depends on the error in the model, obviously, and also how much you change your policy. So if you collect some data and then change your policy to be totally different, now on that totally different policy, the model will probably be very inaccurate, so that's no good. So you need to change the policy by a bounded amount and change the model by a bounded amount. That's all fairly straightforward. But there's another term that showed up in the bound that we had, which is the number of time steps for which you utilize the model. So if I predict 5 steps in the future with my model, I'll get lower error than if I predict 50 steps into the future. That's, again, pretty obvious. What was not obvious is that if you actually look at that bound, the bound is derived using standard proof techniques that people have used in other RL, model-free RL work. If you actually try to find the optimal value for that horizon, you end up with the optimal value being 0. So it says, the proof says the model will result in a better policy. You should have a model,
but don't use it.
Yeah. The proof says you will improve, but the most improvement is obtained by just not using your model.
Right.
We're like, okay, that doesn't seem to make any sense. That defies our intuition. It also defies our experimental results. So to a degree, this is illustrating some shortcomings in the current theoretical tools that we have. But then one of the things that we did is we tried to, that number, the number of time steps, is multiplied by some coefficient, which theoretically, whenever you do theory, you derive sort of the most pessimistic coefficients, right? Because you want it to always be true. But then we try to measure that empirically. We try to actually train some models, train some policies, and measure those error terms and see what do they look like in reality. And in reality, they're not nearly as pessimistic. And in reality, models seem to generalize a lot better than the theory would suggest. So then we did something that you shouldn't really do when you're doing theoretical work, which is that we sort of eyeballed what the actual relationship in the experiments looks like and basically did a linear fit, substituted that term for the theoretically motivated term in the bound, and then we do actually get a trade-off that says that with the actual observed error patterns, you should not use 0-length rollouts. You should also not use very long rollouts. You should limit how many time steps you use your model for, and it turns out that if you actually do that, if you use your model for only short periods, you actually get a much better algorithm than anything that was done in previous model-based RL work, at least at the time when we published the paper. Since then, of course, much better things have come out. So
have you arrived at an analytical relationship between the number of time steps and some characterization of the problem?
Well, yes, except that this is often the case for kind of theoretical analysis, is that there is a relationship and you can derive the optimal horizon, except that it's derived in terms of quantities that are in practice very difficult to measure. So probably the actionable conclusion is that you should use a length that is not too long and not too short. But probably if you're solving a real problem, you're going to select that length empirically.
Yeah. And so does the takeaway is that the later analytical result kind of nullifies the initial analytical result, but in practice, it kind of works the way we would expect anyway. It sounds a lot very hand wavy. Like, where do you attribute value to these sets of results?
Well, I think it works the way we expect it to a degree. I do think that there were some actionable conclusions from it. Like, for example, we did end up with sort of after combining the empirical observation and the theory, we ended up with an algorithm that uses pretty short rollouts from the model, probably shorter than what people typically thought would be suitable, and that did end up working very well. I think it also tells us a little bit about where we should look to next if we want to develop better theoretical tools. So it tells us that you can do some of this analysis, but the current tools gives you a slightly nonsensical result. There's some term, if you substitute in what you empirically measure that term to be into the theory, you get a much more reasonable conclusion. So that maybe gives us some guidance for where we can look to next. And I think that...
Does it also say that we should all shift our efforts to model-based RL as opposed to model-free RL because it's provably better?
Not necessarily. So what does the result say? It says that with model-based RL, you could improve your policy further than you could with just model-free RL. But how much further depends on the error in your model. So in some cases, you can get models with... This is a very obvious statement in some ways. In some cases, you can get models with very low error. In some cases, with very high error. If you can get a model with low error, then it seems like you should use it. If you can get a model... But in some cases, that's very hard to do. So if you have very complex, let's say, image observations, maybe you really just can't get a model that's accurate enough for more than a single time step or even no time steps into the future. So then you're still out of luck.
And so one thing that I often do is maybe conflate the idea of model-based as like incorporating physical world models with what you're talking about, which sounds different, like learn models, almost another type of hierarchical RL. Am I kind of reading this correctly?
So for this discussion, I was just talking entirely about learned models.
Right.
That said, the results and the analysis doesn't really distinguish between them, and there's a very blurry line between them. So if you do have a physics-based model, let's say you have a CAD model of your robot and a physics simulator, and maybe you don't know the masses of some of the links. You can view the process of identifying those masses as a learning process. So you're learning a very small number of parameters. We typically work with much more generic models, so basically neural nets that predict the future. So there you have a very large number of parameters. But in principle, the same lessons should apply to both.
Does this particular research parameterize the relative benefit in terms of number of parameters, or is that interesting for you?
We typically don't worry too much about the number of parameters because we're more concerned with sort of how well we can get this thing to work and how efficiently in terms of data. This is maybe like a little bit of a philosophical point. I kind of trust the systems people and the architecture people. I think they'll build better chips for us, and we'll be able to have lots of parameters. Yeah. And also, in general, in deep learning research, one of the things we found time and time again is that when you have a huge number of parameters, things seem to just work better. And right now, people are actually starting to understand why. They're starting to understand that over-parameterization is actually a very good thing for optimization. So it seems like trying to keep the number of parameters down is not such a rewarding process. So we're more concerned with data, because data comes at a cost, and final performance.
Okay, so this particular result, then, to kind of summarize, is not necessarily an about-face or shift in perspective from the last time we talked. That was very much in the camp of kind of an end-to-end learned approach with a highly parameterized model, a deep neural network as your core model, towards, hey, this result says that we should be incorporating more physics-based models into our RL.
Yeah, it doesn't necessarily say that. Although, of course, if you do have the luxury of having some knowledge about physics, you'll probably have a more accurate model, which means that you'll be able to get more improvement at every step of this process. But yeah, it's really all about how much error you have.
And you've also got some work being presented here on off-policy RL?
Yeah, so this is an area that I've been pretty passionate about for a while, because I think it's important in robotics. It's also very important in many fields outside of robotics. So basically, when we think about reinforcement learning, we typically think about it as a very active process. So if you open up the Sutton and Bardo textbook, you see this diagram. The agent interacts with the world, and then it improves its policy, and then interacts with the world some more. It's fundamentally an online active thing. But if we want models that generalize very well, we want to be able to train those models on large amounts of data, because that's where you get your generalization. So if you want to have very good computer vision systems as part of your RL policy, you need to see lots of images. And it's very hard to have lots of data and to have this fundamentally active online learning process. Like if you need to collect data every time you improve your policy, and you need ImageNet-sized data sets, you essentially need to collect something the size of ImageNet, improve your policy, then throw it out, and then collect it again. And that's just not a very scalable proposition. So what we've been working on a fair bit is this problem of off-policy or offline reinforcement learning. Sometimes they're called fully off-policy. It's also sometimes referred to as batch reinforcement learning. People can't seem to agree on the name. But the basic idea is that you have some data, and in the most extreme version, you're not even allowed to collect any more data. That data is all you've got, and you just have to extract the best policy you can out of it. In reality, we'd probably do something a little in between. We'd use the data and then interact with the world a little bit. But let's just say we were not allowed to interact at all. That's kind of the most rigid formulation. It turns out that a lot of standard RL methods, like Q-learning, for example, while in principle applicable to that setting, in practice perform very, very poorly. And people have tried this before, and they look at these learning curves where you're using fully off-policy data, your policy seems to get better, and then it gets worse. And they look at it and say, well, maybe I have an overfitting problem. Like that looks like overfitting. Why don't I add more data? They add more data, same thing happens. It's like, okay, what is this? An overfitting problem that doesn't go away as you add more data. Turns out that it's not an overfitting problem. Turns out that what's happening is that the structure of the Q-learning algorithm itself actually causes it to perform very poorly if it's not allowed to interact with the world on its own. And it actually ties a little bit almost to that causality point that I mentioned before.
Yeah.
See, in Q-learning, you're making counterfactual queries. People often don't realize this. Where does the counterfactual query come up? It comes up when you calculate a target value, right? Because in Q-learning, you're saying, you took this action, you got this reward, and you're going to land in this state. But then you're going to run a different policy, not the one that was used in the data. So ask your Q function how good that new policy would be. You don't get to actually run that policy, you just have to ask your Q function. So that means plug in a different action. And that action that you plug in is not the action that was taken in the data. And people say, okay, that's okay, the Q function will generalize. And it will generalize if the distribution matches the distribution it was trained on. So you can plug in a different action, that's okay, but you can't plug in an action that comes from a different distribution. And when you optimize your policy, of course your policy is going to find a different distribution. In fact, if your policy can find an action for which your Q function makes a mistake and erroneously predicts a very high value, it will find that because that's what you're asking it to do. So essentially your policy ends up exploiting your Q function. It essentially comes up with like an adversarial action that fools your Q function to thinking that it's a good one. And then because you don't interact with the world, because you don't actually end up trying that action, you never learn that it's actually bad. In the extreme case, you could imagine there's some action that was never ever taken in the data. Your Q function will make some completely nonsensical prediction for it. And if that prediction is large, it's a large number, then your policy will just start taking that action.
Yeah.
So it's not an overfitting problem. It's actually this kind of counterfactual out-of-distribution action problem. And once you recognize it for what it is, then you can actually study possible solutions.
And so why does the existence of this counterfactual problem manifest itself more acutely in offline?
Well, because in online learning, you would still make that mistake, but then you would go and take that action, and then you would add it to your training set. But if you're not allowed to interact with the world, then you don't get the opportunity to do that. We're actually not the only ones to recognize this. There was also some wonderful work by a student named Scott Fujimoto, who also had a paper that studies kind of a similar type of problem. One of the things that seemed to work out really well in our work is the particular formulation for the constraint that you can use to alleviate that issue. And that turns out to work actually very well for a lot of offline problems. So we have the evaluation in this conference is kind of on standard benchmark tasks, but now we're looking to see if we can use it for actual robotics tasks. Another thing that I think is super exciting about this line of work is that once you have this fully data-driven way of doing RL, you could also imagine applying RL to domains where traditionally online active collection is very, very hard. Like, for example, medical applications. You don't want to run a reinforcement learning agent to interact with real patients, but maybe you can get some logs. Maybe applications for e-commerce, for educational support agents, decision-making support, that sort of thing. These are all areas where you can get data, but it's very costly and dangerous to actually have active interactions.
The example you used in describing the off-policy, offline RL was something like an ImageNet. If ImageNet is the data set that you're working on, what's an example of the kind of the problem formulation or the thing that you're trying to learn?
Yeah, so I was maybe a little quick in saying that.
You're just talking about a data set generally.
I meant ImageNet sized.
Got it.
ImageNet is a giant data set that we know enables generalization. It's not an RL data set, it's an image classification data set. But if you imagine that you need similar generalization in RL, you probably need a similar scale. So in the order of, millions of samples.
Sure. And so what are the data sets, for which you are you're experimenting with off policy?
Yeah. So in the paper that we have in the main conference, we, this is just kind of standard benchmark tasks. So we basically took regular RL benchmarks, like the OpenAI GYM benchmarks, and we made them off policy. So that's not an application. That's just a a little benchmarking procedure.
And how do you do that? Do you just have an agent go do a bunch of stuff and then erase a bunch of the data, or
Yeah, we just have some existing agent interact with a task, save the data to disk, and then pretend as though we were given that data.
Okay.
But that's just for testing. One of the things that we've been doing since then, which is not part of this paper, but it's actually something we'll be presenting at a workshop, is actually trying to collect such a data set for real. We actually called it RoboNet, and this was actually kind of a joint effort with a number of different universities. So we had some folks from Stanford, Chelsea Finn and her lab, some folks from University of Pennsylvania, some folks from Carnegie Mellon contribute data to this large data set of robotic interactions. And one of the things that we did that was a little unusual is that it's actually a data set collected from multiple different robots. So these are all robotic arms, and they're all performing kind of similar tasks, relocating objects on a table, moving things around, but they're actually different robots. And one of the things that we studied in that work is, well, first, can we collect this data? Can we make it available to the community? But also, can we train a model that actually is robot agnostic? So you could imagine whatever robot arm you have, you take this model, plug it in, and maybe it will control that robot. We didn't quite achieve that, so we couldn't get a single model that actually generalizes in zero shot to new robots, but maybe somebody else will get to work later. But what we did achieve is we managed to use it as effective pre-training. So you can take all the robots except for one of them, pre-train, and then get a new robot, get a little bit of data, and then fine-tune. And that works so far. And maybe with a data set out there and available, perhaps people can take it and see if they can move towards zero-shot generalization. And of course, since it's a fixed data set, it's kind of an ideal fit for fully off-policy RL research.
Well, Sergey, thanks so much for taking the time to chat with us, give us an update on what you're up to. Sounds like a bunch of really interesting stuff.
Thank you.
We'll have lots of homework to do after this podcast. Thank you. All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.